In today's artificial intelligence class, we will see the passive reinforcement learning. That is another important topic from third unit. And in this topic, we are going to see the direct utility estimation, adaptive dynamic programming, temporal difference learning, and the comparison of all three models. What is passive reinforcement learning? In passive reinforcement learning, the agent policy is fixed. Policy is determined by pi. When come to state S, the agent has already fixed policy of S that determines its action. That is, the policy is fixed for this particular state. So, based on the policy, we have to select the suitable action for this state, right? Okay, let us take chess game. In this game, user have to learn the rules of this chess game before playing. Whether the user is playing well or not, they have to learn these rules. Then only they are allowed to enter the chess game, isn't it? So, this is called as policy. Right here, the agent trying to learn utility function, which is represented by capital U, that is capital U pi of S. Okay, that is utility function for this state, current state. The expected total discount reward, that is, by using utility function, we need to compute the expected total discounted reward. If policy pi is executed, okay, if policy pi is executed in the beginning of state S, right, by the agent, then the agent computes the expected total discount reward for this state. Okay, and this particular agent is called as passive learning agent. This is called as passive reinforcement learning. Okay, the passive reinforcement learning, this task is similar to passive evaluation task. When come to passive reinforcement learning, the agent does not know the transition model and reward function. What is meant by transition model? Transition model is used to predict the next state. Okay, so the probability of P of reaching state S dash. S dash is the neighboring next state, that is the predicted state from state S after doing action A. Okay, this is called as transition model. And next one is reward function, which is represented by capital R of S. Okay, which specifies reward for each state. Okay, and these two things does not know by this passive reinforcement agent. Let us see one example for this passive reinforcement learning, that is 4x3 world. In this 4x3 world, this is 4x3 world, here agent executes a set of trials in the environment by using its policy. Okay, the agent starts with 1,1 this state, and there are two terminal states. The first one is 4,3, this is 4,2, 4,2 is -1, and this is 4,3, 4,3 is +1, that is two terminal state. One is positive terminal state and second one is negative terminal state. If you reach any of these terminal state, the game will be terminated. That means if you reach 4,3, then the game will be terminated with success message, and if you reach this 4,2, then also the game will be terminated but with failure message. And now the agent tries to find the route from starting state to goal state. Here we are having two goal state. First one is positive and second one is negative, as we have already seen. These two are goal state. Okay, now the agent tries to execute a set of trials in the environment by using policy pi. Okay, and the possible actions for our agent is move left, move right, move up and move down. Okay, when come to first trial, okay, the agent start from the starting state, that is for every trial the agent have to start only from this state. Okay, this is the starting state. Okay, after that 1,2. So this is 1 comma 2, 1 comma 3, again 1 comma 2, okay, because we cannot execute, that is we cannot move up direction or left direction. So it will again come to 1 comma 2 and 1 comma 3 and 2 comma 3, 3 comma 3, 4 comma 3. So 4 comma 3 means goal state, that is positive goal state, hence the program will be terminated by using success message. Okay, and when come to second trial, so this is second trial. Okay, it starts here 1 comma 1, 1 comma 1, 1 comma 2, 1 comma 3, okay, 1 comma 3, 2 comma 3, 3 comma 3, okay, this is 3 comma 3, again 3 comma 2, it will come here 3 comma 2 and then 3 comma 3, next 4 comma 3, okay. So it will reach the positive goal state. Okay, again the program will terminate with success message. And now our agent tries with another route. Okay, so the starting state always be 1 comma 1, isn't it? So 1 comma 1, 2 comma 1, so this is 2 comma 1, 3 comma 1, okay, this is 3 comma 1, 3 comma 2 and 4 comma 2, this is 4 comma 2. Once it reach 4 comma 2, okay, the program will terminated with failure message, with the failure message, right. So by using so much of trial, the agent will learn the route from starting state to goal state with maximum reward. Here we are having two diagrams, A and B. Okay. When come to first diagram, it explains the optimal policies for stochastic environment with capital R of S comma A comma S dash, which is equal to minus 0.04. That means the reward point of the current state and the action, then we will get the S dash, that is expected new state. What will be the reward point for this particular action? That is equal to 0.04. Okay, for the transition between non-terminal states. Okay, for all the non-terminal states, if any of the action is executed, then the reward point is minus 0.04. Okay, here two policies here, because the state 3.1, the state 3.1 is here. Okay, both left and up are optimal, that is the agent can move upward direction or move left direction. Both direction if agent moves, then we will get the optimal solution. Okay, next the second diagram is the utility for state 4/3 world for given policy. Okay, that means for each state we are having, see, the reward is, that is the probability is given in each state. Okay, if you are in this particular state, then what will be the reward point, that is what will be the probability to reach the goal state, this particular state. Okay, when come to here, see the reward point is, that is the probability point is very low here, because from here there is a chance to reach the negative terminal state, hence the point is very low. Each transition is annotated with both action taken and rewards received at next state. Okay, the agent used this information about reward to learn the expected utility function associated with each non-terminal state. Here the utility function is represented by u pi of s. Okay, this utility is defined to be expected sum of rewards, that is discounted rewards obtained if policy pi is followed. Okay, so this is what our equation, that is new equation here. that is utility function of current state, which is equal to E of t equal to 0 to infinity. Here t is nothing but the time, 0 to infinity, gamma of t r of st comma pi st comma st plus 1. That is, r means reward point. See, this is nothing but the rewards received when we perform action pi on this state to take the next state. That is, if we perform this particular action, then the agent will reach this particular state, st plus 1. And st is nothing but the state reached at time t when executing the policy pi, okay, which includes a discount factor gamma in all the equations, but in our example, that is 4 by 3, the gamma factor is 1. There are three types of learning in passive reinforcement learning. The first one is direct utility estimation, adaptive dynamic programming, and temporal difference learning. Let us see all those things one by one. Direct utility estimation model. In this estimation model, the utility of state is defined as the expected total reward from the state onward. That means the expected total reward will be updated on each state for every trial from this current state to goal state. Okay, this is called as expected reward to go. That is, estimate the utility function pi of s, that is u pi of s, as average total reward of goals which containing s, that is calculating from current state to goal state. Okay, s is nothing but current state. Okay, so at each trial the algorithm calculates the observed reward to go for each state and update the estimated utility for that state. Okay, so it will calculate the observed reward and that will be updated in that particular state on the table. Hence, the direct utility estimation is an instance of supervised learning. Here, for each example has the state as input and the observed reward to go as output. Okay, this means the reinforcement learning is reduced to a standard inductive learning program. Right. The computed expected rewards at each trial can be applied directly to the observed data. That is, each trial expected utility value will be updated on the table for corresponding state. Adaptive dynamic program, that is ADP, which is model based one. In this ADP, the agent adopt the constraints in Bellman equation. Okay, that means this agent learns the transition model and solve the corresponding Markov decision process. Okay, that means the agent learn the transition model and the observed rewards into the Bellman equation. That is, this is the transition model. Transition model used to find the next expected state, that is the predicted state, and the reward points. Okay, so the combination of these two things will calculate the utility of the corresponding state. Okay, this one. Okay, that is u pi of s, which is equal to r of s plus gamma sum of s dash p of s dash such that s comma pi of s into u pi of s dash. Okay, these equations are linear, so that we have to solve by using linear algebra package. In ADT, the environment is fully observable, hence the learning model is very easy. And here also we are going to adopt only the supervised learning. Here the input is state action pair, that is s comma a, and the output is the resulting state, that is s dash. Okay, and represent this transition model as a table of probabilities. Okay, like this. Now keep track of how often each action outcome occurs and estimate the transition probability P of S dash such that S comma A. That is, if we give S comma A as input, then we will get the S dash. Then we need to compute the probability by using the transition model. Okay, and from the frequency with which S dash is reached when executing A in S. A means action, S means current state. Okay, if we execute action in the current state, in what frequency we have received this probability value of the expected state. So this is called as ADT. And now let us see the summary of adaptive dynamic programming, that is ADP. ADP is smarter than the direct utility estimation, and this runs trials to learn the method of environment. Okay, and it adopts the approach of modified policy iteration, and it updates the utility estimate after each change, and ADP is a model based approach and requires the transition model of the environment. The next one is temporal different learning, that is TD learning, and this is very simpler when compared to our previous methods, that is direct utility estimation and adaptive programming, adaptive dynamic programming, that is ADP. Okay, and it requires very less computation per observation, and it does not need a transition model to perform its updates. Okay, without the transition model, it updates all the table data, and the environment itself supplies the connection between neighboring states. Neighboring states means S and S dash. S is current state and S dash is the expected neighboring state, isn't it? So the environment itself supplies the connection between the state S and S dash in the form of observed transition. Observed transition. In this temporal difference, the environment is uncertain and infinitive. Uncertain and infinitive. Infinitive environment. Okay. Now in this uncertain environment, we need to predict the difference between, that is utility difference between the current state and the next state by using this temporal difference equation. Okay, let us see what is this temporal difference equation. First, the transition function occurs from state S to state S dash via action pi of S. That is, this is the current state. In this current state, we need to apply action A based on this policy of this current state. Okay, then we will get S dash. Then we will get S dash. That is, after applying action on this state, we will get the S dash, that is new state. Okay, now we need to update the utility of this particular state. Okay, that is pi u pi of S. U is nothing but utility state. Okay, u pi of S, which is implies u pi of S plus alpha into R of S comma pi of S comma S dash plus gamma of u pi of S dash minus u pi of S. Okay, this is the temporal difference equation. Here alpha is nothing but the learning rate parameter. Here the update rule uses difference in utilities between the successive states. Okay, so we have to identify the difference of utilities from S and S dash, right, and this is called as temporal difference equation. In this temporal difference equation, this particular portion is called as error signal, and if update, the update is used to reduce the error, that is during the transition function S to predict the S dash, okay, in the temporary environment, that is unknown environment, isn't it? So on those time, to reduce the error rate, we have to use this temporal difference equation, and all the temporal difference method worked by adjusting the utility estimate. This is important, okay, by adjusting the utility estimate when estimates are correct. That is, if we exactly predict the S dash in the uncertain or infinitive environment, and if the utility is correct, then the estimate will be adjusted according to the utility of current state, right? And notice that the update involves only by observed successor state. The TD is a model free approach, and the agent does not require to learn the transition model. Here the agent only updates the states which are directly affected, that is the state which are directly affected, those estimation alone updated here, and based on adjust the values to observed states only, and it is slower but very simpler one in terms of computation. Very less computations are required in TD approach. And now let us see the comparison of all the three learning methods. First one is direct estimation, which is model free. Okay, so this is very simple one, and each update is very fast. That is, each tabulation value updation will be very fast here and does not exploit Bellman constraints. Hence, the convergence is very slow here. And the opposite to direct estimation is adaptive dynamic programming, which is otherwise called as ADP. Okay, this is a model based approach, hence this is hard to implement when compared to direct estimation, and each update is full policy evaluation. Okay, hence it is very expensive one and fully exploit Bellman constraints and fast convergence in terms of times. Okay, hence this is opposite to the direct estimation. And the third one is temporal difference learning, which is also a model free learning like the first one, that is direct estimation. Hence it update speed and implementation. Update speed and implementation are similar to direct estimation because this is also the model free one, isn't it? Okay, the partially exploit Bellman constraints and adjust the state to agree with the observed successor. Okay, so this lies between the direct estimation and adaptive dynamic programming. Okay, that is, the convergence lies between direct estimation and adaptive dynamic programming in terms of time. So far we have seen the passive reinforcement learning. Here we define this passive reinforcement learning and explain by using the example 4x3 world. After that we have seen the three different approaches, that is direct utility estimation, adaptive dynamic programming, temporal difference learning. After that we have seen the comparison of all three approaches. In the next class we will see active reinforcement learning, and for more information please go through your textbook. Thank you.